Oops. Okay, thanks. All right, so we covered, probability so far. We're going to do a little bit more before we get onto the actual, nitty gritty of what I want to talk about. So I only talked about one feature for the Gaussian, distribution, right? But what if we're dealing with multiple features? I'm only done with one feature. What happens if we have several features like you're dealing with in your lab, right? So each of the features might be Gaussian distributed, and then each of them have a different mean and variance. So you're not guaranteed that each of them will have the same mean or the same variance unless you normalize. We'll talk about that later, but initially they may have different means and different variances, right? And the features can be dependent on each other. So the way that one feature is created was based on how another was created. So for example, if you're using polynomial features, like you have, a set of x and then you cut up x squared and x cubed, they're relying on another feature, right? You have features that are dependent on each other. So what's the PDF of this? Like, what's the actual probability distribution function of this? And we're going to use what's known as the multivariate Gaussian PDF. So this is the general rule where you have an n-dimensional space. There is a Gaussian probability distribution function that spans n dimensions. Okay, so given an input vector of features, x, right? So x1, x2, all the way up to xn, there's n features, right? So this is a column vector. So this is a row vector, but I'm going to do t to denote the transpose, and the means of each feature. Okay, so I'm going to call this mu. Okay, so this is also a column vector as well. So given an input set of features, given the means of each feature, and we're also given what's known as the covariance matrix. So this is a matrix that tells you how related or how correlated features are, given your training and your test data set. See, so sigma of. So it's an n by n matrix. Okay, so it looks like this. So you're computing the variance of the first feature, the variance of the second feature, all the way down to n, and then we have covariances, right? Right, so this would be n. Okay, so sigma I squared, this is the variance of feature I. Okay, and sigma ij, this is what's known as the covariance between features I and j. Okay? So naturally you could think that, the covariance between I and j is equal to the covariance between j and I. It naturally makes sense. So if you're trying to find the relations between, variables 1 and 2, it's the same as finding 2 and 1. It's, it's pretty straightforward. So if you want to compute the covariance, simply equal to 1 over n minus 1. And this is k equals 1 to, let's do m. Sorry, we're going to do training examples. Okay. X I k and x j k. Okay. So this is mean of feature I, and this is mean of feature j. Okay, and then you have m examples. Okay, and then and this is pretty, yeah. Okay, and then these and this guy. kth examples, ith and jth feature. Okay, so it makes sense. If you were to flip them, if you did sigma ji, the products are commutative, so that's why they match up. Okay, so this is what the covariance matrix would be, and then finally, this is what the definition of multivariate will be. So here's the definition. Okay, so probability of the random variable x. So we're x, and then this is parameterized by mu and sigma. Okay, is equal to, that's going to be a little bit of a mess, 1 over 2 pi for 2. Okay, and then exp stands for the exponential, e to the power. This is transpose. Yeah, not the most pretty equation, but, gets the job done, I suppose. So that's what this is. Okay, so your input vector x is assumed to be, set of features, x1, x2, all the way up to xn, right? There's n features in total. This guy here, when you're using the vertical bars, this is what's known as the determinant of the matrix sigma, and then you're taking the square root of that term, okay? So there's n features, and then you're doing, 2 to the power n over 2, and this guy here, this is the inverse of the covariance matrix, okay? So determinant, so it's, it's not the most pretty equation, but that's how it's defined, okay? So what this means is that if you have an n-dimensional vector, this would be the probability that that particular set of features that will be bound to happen when you take a look at your data set. So probability that the event x will happen given by the mean and the covariance matrix, okay? So the covariance matrix is nice because what it does is that it allows you to find relationships between vectors. So it can determine whether or not you have features that are correlated, non-correlated, and so on. So from sigma, let me just go to full screen so you can record this. So from sigma, we can find relationships between features. Okay? So the diagonal tells us the variances of each feature. Okay? Tells you the variances of each feature. So that's sigma squared I. So now let's take a look at sigma ij. This is the covariance. Okay, so there's 3 possible values for this. If this is equal to 0, what this means is that there is no correlation between the features. So feature I and feature j are completely random. There's actually no way that feature I generated feature j in any way. There's no correlation between them, which is what we'll generally assume when we take a look at the score. So each feature that you're looking at is independent of everybody else. So this means that no correlation. Between features I and j, okay? Now, if you get a positive number, what this means is that if feature I increases, feature j also increases. So if you were to draw like a linear line between them, if you went 2 one way, then j will also increase by a linear factor, whether it's 2 times or 4 times, but it will increase when I increases. Okay, so if this is positive, this is what is known as positive correlation. So what this means is that if feature I increases, then so does j. Okay. Similarly, if it's negative, this is what is known as negative correlation. So if feature I increases, then feature j decreases. And I'll show you some pictures, of course. If feature I increases, then j decreases. All right? So another thing that I'd like to talk about here is when you have no covariance and the covariance is 0, these are what are known as the features are independent. So however a feature I was generated had no bearing or no effect in terms of how J was generated. Okay? So here's a special case. Okay? If all features are independent, what's going to happen is that all the covariance matrix terms, like all the off diagonals, are going to be 0. So the only things that are non-zero are going to be the diagonals instead. So if all features are independent, therefore sigma is diagonal. So what I mean by diagonal is all the off elements are 0 except for the ones that are along the diagonal. So sigma 1, sigma 2, all the way down to sigma n, and then this is all 0. Okay? So that's what this means. So all the off diagonals are 0. Okay? So therefore, what will happen is, because this is diagonal, the probability will simplify to this. Oopsie. I don't like this thing. I'll let you do the math yourself, but it looks like this. So, actually no, I'll go ahead and do it. So if it does this, it simplifies to the following. I'll let you do the math on your own, but let's see. So this becomes a product of individual Gaussians. So what it's going to look like is it'll look like this. So the pi is the product, and it looks like this. And then okay, I'll let you do the math on your own. So if you were to take this and if you were to plug it into that multivariable thing, if you were to simplify it, I won't do the math, I won't bore you, but it actually simplifies to this. Okay, so if every single one of your features is independent, then the probability distribution function multivariable is simply just taking each one of the features, building an individual Gaussian, and just multiplying them all together. So that's what it would be. So, so let's see. So sigma I is the variance of feature I. Okay, and mu I is the mean. Sorry, of feature I. Okay. So that's what happens. So it becomes a product. So that they're all independent. And this is obviously input vector, input feature vector. So x is equal to, 1, 2, and all the way up to the end. Okay, nice. So let me just show you a couple of pictures, before we get started. So let's see here. Let's see. Yeah. Okay, here we go. Here. Here's an example. Okay, some examples. Okay, so this is what happened. This is with two features, x1 and x2. Okay, and in this particular case, the mean is centered at 0, 0. Okay, so x1 and x2 is 0, 0, and the covariance matrix is just identity, 0, 1, 0, 0, 1. Okay, so these are equal to 1. Okay, so in 2 dimensions, this is what the curve looks like. So on the left, this is what the probability looks like. So you have x1 here and x2 here, and the height would be the probability that those two features happen, at the same time. And this is what a contour plot looks like. So you can think of this as taking individual slices of the peak and projecting them onto the z-plane. So this, you can think of this as, going underneath. So you can think of this as like a construction cone. And what you're doing is you're taking a look at it underneath and taking a look at what. So you're looking at it from underneath and seeing what all the heights look like. And this is what it is. So you have the mean vector here, and the features are spread out like this. So this is what happens when the features are independent. Okay, that's nice. So this is what it looks like. So you have x1 and x2. All right. So let me just show you some more pictures. So this is the canonical distribution, and let's see what happens when I scale, the covariance by 0.5. So mu is equal to 0, 0, and the covariance is equal to 0.5, 0.5. Again, this is all independent. So what you're going to notice is between this guy and the top, you'll notice that the width has changed. It's smaller. Okay, so this is the spread for sigma 1. This is the spread for sigma 2. And you'll see that the widths are smaller. For sure. Because if you take a look at this one on the left, you'll notice that the spread between them is actually smaller. So this is what happens when it, of course, is independent. Okay? And this is what happens when I decide to change the spread a little bit. Instead of making it 0.5, I'm going to change it up to make it look like it's 2 instead. So the covariance matrix is 2. Again, these are all independent features. So again, this is all 0, and then I'm going to bump the width up to 2. And then you can see here for sure that it's actually widening out. So it's much wider than before. So this is, the width is a little smaller. And then here, the width is larger. And you can see that the contour plot, the extent is wider as well. So this is, 2 and then 1, right? So widths are larger. Okay, so this is assuming that the features are independent. So let's say there is some correlation between them. What happens if I decide to introduce some correlation in between, inside? So let's see. Okay. Actually, before I do that, I'm gonna introduce something. I'm gonna do something else here. So let's do this. I'm gonna introduce something else here. So let's say the mean was 0, 0 again. And what's gonna happen is that I'm gonna make one of the variances slightly thicker than the other. So it's gonna be 1 for the x1 and 3 for the x2. So this is what happens here. So what's gonna happen is that, this is sigma 1 here, right? And sigma 2 is gonna be wider. So that's what happens. So when one of the features has a larger variance, if you were to plot this distribution, you'll see that the vertical is larger than the horizontal. Okay? So x2 has a larger spread. And you can see it through here. It's like if you were to drill like a contour plot, it looks like that. Right? So if you were to slice it, so you can see that it's oval shaped in the vertical direction here. All right, and then let me show you another one. Right? Yeah, this one. Same situation, but I've reversed it instead. So this is 3, 1, 0, 0. Okay, and this is sigma 1 and that's sigma 2. Okay, so you can see that x1 has a larger spread. See, so if you were to do a contour, it looks like that. So if you were to take individual slices, it looks like that. Okay? And we've got a couple more for you before we go on. It's always nice to see pictures. And let's introduce some correlation. So this is what happens when I have features that are correlated. So the mu is the same, but what's going to happen is it'll look something like this. So you have the variances themselves are okay, but the covariances are 0.5. Okay? Now if you take a look at what happens if x1 increases, then x2 also increases by a factor of 0.5. So you can see that there's a line going this way because as x increases this way, then x2 will also increase as well. So this is what happens when you have correlation in features. So let's see, just check here. Okay, so the off diagonals. So there's positive correlation. Right, so it kind of looks like this. So it's kind of off on a 45-degree angle. And then let's say I have negative correlation. So instead of 0.5, I've got minus 0.5. So when that happens, you expect the curve to go the other way. So there's a negative correlation this way. Right, so when x1 increases, then x2 will decrease. Okay, so the covariance matrix to generate this is just minus 0.5. Okay, and it looks like that, and the contour plot kind of looks like this. All right, and then finally, just one more, just to be sure that this is what happens when we move the mean. So, for example, let's see here. Let's say this one. Oh, shoot. Undo new page. Okay. I'm just going to do one more just to be sure we're on the same page. So let's say I decide to move the mean instead. Okay, here, this one. Okay. The covariance matrix here is unity, all right? So it's the same, but the mean is changed. So x1 will be -1, and x2 is -1.5. Okay, so the mean is right over here. So the mean is changed. So the variance itself, this stuff stays the same, right? So this stuff here is just the same as before. It's just the offset of where it actually happens just changes. So this is what happens in 2 dimensions, okay? So it's not so bad. So I just wanted to show you some pictures so you can see what it looks like. So if you were to, take a bunch of, input training examples, then if you were to plot the distribution, it would fall under that kind of distribution like that if you were to draw it. Okay. And that's all I got here for that. Okay, yes? It's impossible to visualize, unfortunately. So you can't. And so what you can do, you can make it in 3 dimensions where each feature would be a point, and then the color of the point would represent the probability. So you'd have like a color map where blue would be a low probability and red would be a large probability. So you can do 3 features, but it's a little hard to interpret because you have to take a look at the color at each point. When you're visualizing, it's hard to go beyond 3. When we take a look at later on in the course, we're going to take a look at a topic which is called dimensionality reduction, which will take a bunch of, will take features of n dimensions and compress them so that they look, and compress them so that they're 2-dimensional, so you can visualize what the 2-dimensional equivalent would be. That'll be next month. It's called dimensionality reduction. It's actually a pretty cool topic. But yes, it's a very good question. Thanks for asking. Okay. All right. Now we're going to get on to the meat of the course, Bayesian decision theory. Okay. So Bayesian decision theory. So if you remember classification, recall classification. Okay. Classification is what? So far we've mainly discussed, trying to find the right set of parameters that'll distinguish between one class or another. That's logistic regression and classification. Right? So far we have discussed finding the right parameters, given a training set, okay? And the goal is to classify a new instance to belong to a class, I guess, all right? Okay, so the objective of this was to find a decision boundary. So the whole goal of logistic regression is to find that plane or to find that line that best separates between one class and another if you were to plot it on a grid. So find a decision boundary. Okay, so that's the point of that. Okay, so we're going to take a look at this differently. So now let's look at it differently. And for the purposes of this course, we're going to only look at binary classification. We can do multiple, but it gets, I don't like the math behind it, and I'd rather emphasize on stuff that is actually used in practice. Like Bayesian decision theory is sort of used, but I don't see it used quite often. But it's part of the course curriculum, so I'm going to cover it. So binary classification for now. Okay. So what we're going to do is we're going to take a look at this probabilistically. So we're going to consider all the features as being random variables, okay? So what Bayesian decision theory means is that you want to find the probability that, you have a probability model for one class and a probability model for another class. And the class that you choose is the one with the higher probability. So that's the whole purpose of Bayesian decision theory. So you're not looking for a decision boundary anymore. What you're looking for is the class that will give you the highest probability that it belongs to that particular class. Okay? So binary classification for now. So consider features as random variables, as we talked about before. Okay, so the positive and negative classes have associated features. Okay, so we can build different probability models for the positive values and the negative values. Okay, so what we can do is build a PDF for each class. All right, so build a probability model. Okay, so in this course, as I talked about, the features of Gaussian distributed. Okay, so to figure out which class a new instance belongs to, okay, find the probability that the instance belongs to either class, right, and choose the class with the largest probability. So logistic regression and all that, they're what's known as discriminative models or discriminative classifiers, because you're trying to find a decision boundary that classifies between the two. This is what is known as a generative algorithm or generative model, because what you're doing is you are using the training set to find a probability distribution function for positive and negative classes, and then given a new instance, you're taking a look at the balance of probabilities. So if one has a higher probability than another, that's the class you choose. This is what is known as a generative algorithm. Okay? So that's pretty much the crux of Bayesian decision theory. Okay, so choose the one with the largest probability. So here are some definitions before we start. Okay, so unfortunately this is very notation intensive, so I'm just following what the convention would be. So we're going to let omega j be the jth class. We want to classify and input into. Okay? So for binary, that would be just, we're going to do with one notation here. So omega 1 would be the negative class and omega 2 would be the positive class. Right? To classify into given its features. Okay, so for binary, we're going to take a look at omega j, where j is equal to 1 and 2. So this is the negative, and this is the positive. Okay, cool. Okay, we're going to take a look at just positive for now. Positive, negative, binary for now. Okay, so this is the first definition. The next definition is what's known as the prior probability. So this is what's known as the prior probability. Okay, so what this definition means is that how likely would you choose this class if you knew absolutely nothing about the system? So if you had a problem in front of you and you had a bunch of features, like you've had if you had a bunch of input points and you had a new point that you haven't seen before. So given those input points, you build a model. How likely would you take that new instance and put it into class J? So how likely would you do it if you had absolutely no idea what to do? And this is what's known as the prior probability, because you don't have any information. You're just, okay, here it is. What would you do if you had absolutely no information beforehand? So how likely will the new instance belong to class J, okay, without any other information? I'll give you a little intuition behind this. So let's say I had a whole bunch of numbers. Let's say it's between 1 and 3, right? And let's say that a good majority of them, let's say 90% of them were 1s and 10% were 2s. So if I were to be given a completely random number, how likely would you classify that number to belong to 1 and 2? Well, if you have a whole bunch of 1s, a large distribution of 1s, then you're probably more inclined to say that I would probably put this into a class of 1 because there's so many of them. It's probably more likely to classify it as an input to be 1. So how you compute the prior probability is quite simple. All you have to do is for each class, you just calculate the fraction of the particular inputs, the fraction that each input, the class in terms of the fraction in total. So for example, if you had, let's say, 3 inputs that belong to class 1 and 5 inputs that belong to class 2, the prior probability would just be 3 over 8. So it's the fraction of each, it's the fraction of all the inputs that belong to one class divided by all the inputs in total. Okay, so let's see here. Let's see. Prior probability. Yep. Okay. Just taking a look. Prior probability. That's fine. And then in practice, the prior is computed by the fraction of inputs in the training set that belong to class J. Okay, so this is simply number of examples with label J divided by number of total examples. Or total number of examples. My grammar's not good today. Total number of examples. Okay? So that's how you compute the prior. So you just count how many training examples that belong to the label that you're looking at and just divide by the total number of examples. So if you had 75 of class 1 and 25 of class 2, then the prior would be 0.75. There's 75% likely that you put it into class 1 if you had absolutely no idea what was going on underneath. Okay, so that's how you calculate the prior. Okay, and if you want to calculate the next part here, so let's see here. Okay, it's 3. So I'm going to talk about this. Okay, so this is the likelihood, or the class conditional probability. Okay, so what you're doing here is to compute this. Each class has a PDF. Okay, so what you're doing is you're going to compute the mean and the variance of each feature of each class's features. Okay, and then what you do is you build a PDF. So for example, you would have maybe something like this. So if you had, let's say, probability of belongs to class 1, it would be this guy. This is let's assume one feature. So this is an example. This is one feature. Okay. Sorry, this is 1. Okay, and then you'd also have belonging to class 2 as well. So there's 2 different probability distributions for each class, and it has a different mean and variance because you're using different inputs to classify, to get the mean and the variance for those features. Okay, so mu1, sigma 1 are mean and standard deviation. Actually, just do variance of negative class features. Okay, and then similarly the same thing. Same, but for class, or the positive class. Okay, so that's how you build a likelihood. So what you're doing is you're building a model where you're computing the mean and the variance of the features that belong to the positive class, the features that belong to the negative class, and then you build a PDF for those. So you're building a discriminant, you're building a model for that. All right? So now that we have these things, what we need to do now is, let's see, to finally determine the, which class, actually not like the probability of, let's actually, no, to determine, that's not the probability, let's say to determine which class, I'm going to start off with that instead, which class an input belongs to, you find the posterior probability. Okay. I'll take another break in 10 minutes. Okay. So you find the posterior probability. So okay, so this is what we're doing. So we're trying to find the probability that we want to classify the input to belong to class J given the input features. Okay, so find probability of putting into class J given input X. Okay, so if you recall Bayes' rule, it's pretty much this. This is Bayes' rule from before. Okay, so this guy's the likelihood, and this guy is the prior, so this is given. We know this already. Okay, this is the evidence. We don't know this, but it's actually easy to compute if you remember the law of total probability. So this is, let's see, it was J from 1 to C, that's the number of classes. That's if you want to do that, that's fine. And this is all given as well. So this and this are given. So then all you have to do now is you compute this for the first class, you compute this for the second class, and see which one of them is larger. So if the probability to take an input and classify it into class 1 is larger than class 2, then you put it into class 1. So it's a balance of probabilities. You choose whichever one is the more likely case. So let's see. So, that's fine. Okay, that's good. I'm jumping all over the place. So, okay, that's good. All right, so let's see here. Therefore, you calculate P and P. So you calculate, the probability that it would belong to either class 1 or class 2. And choose the higher one. Choose whichever class has the higher probability. So that's basically Bayes' decision rule. So you're calculating a balance of probabilities. Whichever one is the larger one, then that's the one you choose. Okay. Just going to diverge a little bit. Gaussian distribution functions. Or Gaussian, not distribution, sorry, discriminant functions. Okay. Okay, we're going to take a look at the binary case by itself, just the binary case. Makes things a little easier. Okay, so if you recall, this was the multivariable PDF. It was so this is 2 pi n over 2, and then this was square root, and then we have, let's see, it was minus a half, x minus mu transpose inverse, and then finally this again. Okay, so this is the multivariable. Okay, so usually in practice, what we do is, even though we have different means of each of the features, we usually just calculate one covariance matrix, just in practice. So what I mean by one covariance matrix is that even though you compute the average, or you compute the average features for the positive and negative class, to calculate the covariance, what you do is you consider every single training example, and then you find correlation between all of the examples instead of just doing it for positive and doing it for negative. You do it as one huge matrix instead. It's the accepted practice. So usually we just use one covariance matrix to describe both classes. Okay, so what I mean is to find the covariance matrix over all features for both classes. Okay? However, each mean or each feature or each class has its own mean feature vectors. So mu1 and mu2. All right? Okay. Okay. So what we could do now is we can create two probability models, right? One for positive and one for negative. So we're going now to multivariable, and then you just choose the one that is the likelier, that's is the more probable one. Okay, so we can. Let me just finish this up and we'll take a break. We can create two probability models. Sorry, come on. Let's see how much time it is. 1, 2, 3. Okay, good. So I should be able to finish this up today, or, good. Where the probability of an input set of features comes from the positive and negative classes. So this is the likelihood. Okay, so basically you just copy this and do it for both features. Okay, so there's two of them. So the probability that we belong to the first class is simply, oh sorry, I'm just going to take this out. Okay, so you have sigma is the same, and then the mean features are different, and then you do the same thing for this guy. Sorry. Copy. Okay, that's not what I wanted. There we go. Yeah, Windows Journal is a little temperamental at times. So this is 2 and 2. Okay, so there's two different models here. Okay, and then so you have that. That's fine. Okay, that's great. And then what we want to do now is we wish to find the posterior probabilities, right? And then figure out what to classify them in. So P1. Okay. Decide which class the input belongs to. Okay, so you have a very easy decision rule. So the decision rule is this. All you got to do is just check to see whether or not the probability of going into the first class is bigger than the probability of going to the second class. And if that's the case, then just choose the first class. And then if not, choose the second class. That's really what the rule is. And this is what we talked about before. Okay? So if you remember, so let's see here. So let's find, so choose that. And then what you do now. Okay, so if you recall, this was straight off from Bayes' rule, right? Okay, and then similarly, we can do that for the second class as well. So now if I were to take these guys and plug them into here, right? You're going to notice that there's a p of x term that we can simply get rid of. So therefore, if I had, you know, this was x, sorry, not, can't write today. This is p of x, right? And then okay, the denominator we actually don't need anymore, so we can cancel these out because common factor. So it's not needed. Okay, so therefore, your decision rule is just this. So therefore, decide W1 if you're just using the likelihoods and the priors, which is nice because you don't need to compute the evidence anymore. Okay, and then else W2, and that's it. And I'll get into how to compute these later on. So these are both given, right? So this is the likelihood and that's the prior knowledge. Okay, so one, two, three. Okay, so I'll take a break here and we come back and then I'll finish off.